Today I want to talk about pipelines much more than just the model. I assume you've seen some graphics, something like this, where machine learning is represented as a pipeline, and we talk about machine learning pipelines. They may start in different places. For example, with model requirements, we want to build a model, then we collect some data, we label that data, we maybe clean data, we do feature engineering, we do model training, we do model evaluation, then we deploy it, and then we monitor it. So kind of sequential steps. You might skip some of those steps if you have a foundation model, right? So these days, a lot of projects don't do a lot of custom data collection or maybe just collect test data. But in general, that's kind of a common view of data science. And I may have mentioned this earlier that typical machine learning class focuses pretty much on the last steps here. Like you train a model or you build the algorithm to train a model and you evaluate accuracy and then you're done. With ML ops, we worry a lot about automating this, automating the deployment, maybe monitoring this. We will talk about this next week. And there's all this realization that there's all this infrastructure around just the model. This is a paper that's essentially I think I make you read this later. This is kind of the start of ML ops, before this ML ops was a term, where Google, including a team here in Pittsburgh, realized that the maybe 100 or 200 lines of TensorFlow code was not a lot of code compared to all the other infrastructure that they were writing. Right? They were writing a lot of infrastructure just to serve the model, just to monitor the model, to deploy it across many machines, to do feature extraction. This was nearly 10 years ago, and by now a lot of these boxes have shrunk. So in a way, you don't write 50,000 lines of code for model serving. You pick an open source library to do this for you, but there's still complexity in that you need to figure out which library, how to use it, and so on, right? So the complexity is still there. And I think what I tried to convey earlier is that all of this machine learning pipeline there is in the end to produce a component in a system, right? So the pipeline is there to use to create a model that can be used. And then we also want to use that model to do something useful. But today, let's focus only on the pipelines. The pipelines themselves can become very complicated if you use them in practice because it interacts with so many other things. So data collection sounds easy. In a course, you typically give them a data set, so you don't do this yourself. But in practice, you might look around and find public data sets, but oftentimes you collect data in your own system. So you may have something deployed already. Let's say your Facebook, you know what people are clicking on. You have millions of log files and you're trying to extract data from that, and that's going to be your training data. Somebody needs to label that data. If you do traditional supervised machine learning, that's typically outsourced. Data scientists don't like to label data, right? It's a very tedious job. And data scientists are very expensive, so we pay the lowest we can get by outsources to somebody somewhere in the world. It's not a very pleasant job, typically, data labeling. There are ideas of partially automating the labeling, weak supervision. You may have seen something like Snorkel, using models to do some of that. There's a lot of knowledge in crowdsourcing that you don't trust just one person, but you have multiple people label this and kind of dynamically figure out how much you can trust them and so on. We're not going to talk about that much here. But then data cleaning, feature engineering, there's often things that you want to reuse. There's expertise in how to do this, infrastructure. And then there's often a lot of distributed system, distributed computing thing to actually do this at scale. We will talk about this much later. Training, you often have massive distributed infrastructure if you train something large. For evaluation, you often integrate this with A/B testing infrastructure, and so on and so on. So I don't care so much about the details. The point that I'm trying to make is that in practice, this pipeline, which seems like a very simple kind of sequential step, is often deeply integrated with other parts of your system. So you often have very deep things that chain it to other parts of the system, and the system changes over time. Your requirements change over time. A classic machine learning pipeline that you see in a lecture is just a notebook. I assume that's something that you use all the time for model development, right? So you load data, you clean data, you train a model, you evaluate the model, all within a notebook. And that usually assumes that you have very little dependencies, not much changes. You're not really deploying that. Do you like notebooks in general? I was raised on IDEs, and notebooks are kind of really weird and kind of, they got better, but kind of really bad tool support, like auto-completion only came in the last few years, things like this. Had a comment? Or? Oh, you like notebooks? From a software engineering perspective, they're kind of weird. They also have this weird mechanism where you can execute a cell repeatedly and everything is global state, essentially. We'll talk about some of this later too. How about using notebooks in production? There's actually people who suggest this. There are blog posts about this. There are tools. You can NB converts a Jupyter notebook into a Python script, then you can run this. People have run this in production. I would argue this is not a very good strategy if you have lots of dependencies and you actually want to maintain or test things. Real pipelines get complex, large amounts of data, distributed storage, special hardware needs, fault tolerance, humans in the loop, and so on. So you really want to think about how can I develop this in a very robust way that it just doesn't run once on my machine, right, with my current dependencies, but that I can execute repeatedly. There's a common problem with silent mistakes where you run a pipeline repeatedly and something goes wrong and it's very hard to notice. Has anybody experienced this? Probably more in an internship than in a class project, but what are examples where something silently goes wrong in a pipeline?
It's not very like ML infra, but I had this issue where it was like an ETL process and the file came in late. So then the process just didn't run.
Sorry, the file what?
So like the file had to come in, had to get processed and then sent. File just came in late by like.
Okay. So if something runs on a schedule or so and you just rely on the file being in a specific place, if that file is late, you might just run on the older file or it might just crash. Crash is actually nice because then you notice. The problem are often silent mistakes where it just runs because it has the old data, but now it trains last week's model again. There are lots of these kind of stories where a pipeline uploads a model to a server at some point, but the model has gone bigger and bigger over time and there's not enough space on the server, so the upload just fails and you just keep running the old model because you didn't notice. Lots of stories where a pipeline just broke and no new data came in and nobody noticed. Machine learning libraries are often designed to handle a lot of noise and deal with a lot of kind of problems. Like a machine, if you train with TensorFlow, it will typically not crash. I mean, it can do that too, but it will maybe produce a model. If you engineer the features poorly, it will produce a low accuracy model, but it will not crash, right? Crashing mistakes are actually really nice in traditional software systems, but this is often done in a very robust way. So there's lots of these examples of something just silently going wrong. And people trip over this all the time. So one thing that you really want to do, if you want to deploy pipelines, design for change. Things will change and you want to test things. So traditional notebook code, this is just a file, is kind of a long sequence of just a bunch of statements, right? There's very rarely any functions or abstractions in a notebook, very rarely any test cases. And if you look at code like this, it's even hard to think about how would you test that in the first place. How would you test something like this? You can run an end-to-end test where you essentially run the entire notebook and see whether the result is the same or is above a certain accuracy level. Is there anything more that you can test in there?
Maybe separate the code into like different cell blocks so you test like block to block instead of just once running everything at once.
How do you test? Yes, you can look at one block at a time. right? Testing, I assume, means executing it and looking at the output manually, right? Is there something more repeatable? Something that we could run after every change where I don't have to stare at the output? I assume you've all written unit tests in some form, right? Where you write a short piece of code that executes some function and then it either passes or fails. Can you write unit tests for something like this? So we're going to make you do this for the second milestone, not for the first. For the first, we don't really care about your code quality. But you really want to separate your pipeline code into individual functions, and then you can test those functions. This is actually something that's in software testing known to be, you want controllability and observability. You want to be able to control individual pieces of the infrastructure, execute them in a very targeted way, and then be able to see whether the behavior is as expected. This linear long code without abstractions is very hard to test because you have no entry point here, and you also have no outputs that you can really test. I mean, you could look at outputs of individual lines in a notebook manually, but it's very hard to write assert statements. Once you start breaking it down, now you have individual pieces that you could test, right? So now you have a thing like encode the day of the week. It's some data wrangling code where you encode something to massage the data in a form that the model can understand. And once you have that as a function separately, you can test that. You can test whether your code is right? You can provide some inputs and see whether you have the expected output for those transformations. And data wrangling code tends to have a lot of mistakes. Again, these mistakes usually don't crash. So here, 3 code snippets. Each of them don't do what the original author probably intended. Any idea what's wrong? What does the first line do? All right, let's do the second one. That's maybe slightly easier. What does the second one do? If you execute it, what changes? What?
As a dictionary of all the things that it's supposed to have to.
Oh. What if I tell you that nothing changes if you execute that statement? The data frame is exactly the same after as before you execute that statement. You execute a lot of code, but nothing changes. Why? Right, so it creates a copy. You can assign it once, but if you create a copy of a copy, you modify that copy, but not the original. And I'm not an expert in any of this, but fairly common mistake. What does this code do?
But
That's what it intends to do.
float value can get converted to 0.0 and then throw an error.
That's what it intends to do. What does it actually do?
Points and
It does nothing. Why does it do nothing?
It's an as-type function, but unless you assign it to something, it does not.
Yeah, it's not an in-place operation. In this one here, if I remember correctly, there's the idea that you take the joined column, you try to drop all the NAs from that column, and then you modify everything else. But if I understand this correctly, drop NA takes the entire rows, takes out the entire rows from the entire table, not just from that column temporarily. So it actually removes data from the table in a way that you probably don't intend to remove it. So I'm not showing you this to test your knowledge of the API of pandas or whatever this is, right? This is just, these mistakes are super common and these are super easy to make and they're very hard to notice because they're silent mistakes, right? Nothing crashes here. You can execute these lines just fine. And unless you really look at the output and see whether it has changed in the intended way, you might not even notice. And then you put it into the machine learning model in the next step, and it will train a model for you. It just trains it on the wrong data, and it's maybe slightly less accurate. And maybe worse, in production, you use the correct data encoding, right? So the model has seen different encoding during training than during inference. Do you want to do more of these, or are we good? I can go on for a while. The first one I think is super obvious, typos. But again, it fails silently, right? You just have another column. This one I think is a nice data modeling mistake. This is from an Android data set in a competition where data is provided as 70,000, 70K or 70 million M. And there are fun corner cases here of how this works or doesn't work. So the idea is to have 70K and have that translated to a number. And it works in most of the cases until one data point is 7.5K. Right? That doesn't work. There's other examples for the same thing where they use upper level K here, uppercase K here, but the correct thing in other places. Silently again fails, just does the wrong thing. This is the same problem as the previous one. And so again, data wrangling code is easy to get wrong. So doing some sort of testing like this, especially if you care about this code in production, right? If this is not just a quick prototype for a competition, might actually be quite useful. And to get there, you actually have to separate the code and make it testable. Does this make sense? So for the first milestone in the team project, go ahead, use a notebook. For the second one, we expect you to convert this into scripts that you can actually test. So not just test the models, but test the system. I want to briefly just talk about that the way we are using pipelines these days probably changed quite a bit. So modern AI pipelines, especially in the last few years, focus way less on data wrangling. You still do this in a lot of cases, but way less on model training, a bit more on fine-tuning, but even that's kind of rare, and much more on prompting. And often with multiple LLMs, right? So you have something, this is maybe a much more common kind of approach where you have a prompt template. Like, tell me what the sentiment of the next email is with a placeholder for the email. You get the user input, you concatenate this, and then just run it through an LLM, right? Even there, you have some code that needs to process this and kind of compute this. Maybe you want to test this. Has everybody seen RAGs before? So this is just the idea that in parallel, instead of just putting it directly into the model, the input, you find related documents. You could do internet search. Typically, they use something more fancy, right? Some vector database or something. But in the end, it's just some search to find relevant content in a database or in some document thing. And then you just concatenate this as a prompt, as additional information, right? That usually gets models to have more knowledge that it hasn't been trained on. So again, you need to connect it to other databases. So to my previous point of interacting with other components, the pipeline is not in isolation, right? So it needs to understand the storage, and you kind of need to still think about model evaluation and monitoring stages of the pipeline. Multi-step pipelines are pretty common these days, where you may have something like, first a model decides, should we ask a RAG, yes or no? And then based on that, you go in different directions. It's quite common to ask a model to do something, then ask the model to refine it in a step. This makes it more expensive, but allows to build more capabilities. So again, some sort of these kind of approaches that integrate with a bunch of different systems, machine learning and non-machine learning, extra databases, and so on are quite common. So they're quite complex. And then agents we talked briefly about earlier, and that's what apparently everybody cares about right now, is inverting the control essentially, right? So you give a task to an LLM, but then you let the LLM do the planning and you interpret the output of the LLM to determine what the next steps are. So the LLM could ask the system to call a tool. With coding agents, you probably see this most, but it could be look up information, could be search in this database, could be send an email. And typically the way that this works is you run the tool, the output of the tool gets concatenated to the context, and you ask the model again, am I done or what should I do next, right? So you give much more control to the model. It's kind of this inversion of control thing where the model is in charge rather than you. But again, the point here is that it now even more explicitly interacts with all kinds of the system, right? So you give it direct tool access to numerous external systems, even humans. And these are all complexities beyond the original pipeline that you might want to test at some point. So coming back to this, so we have all these kind of code bases, whether it's the traditional pipeline or now the integration in a RAG or the integration with tools, right? So there's so much code around the model that you really want to test. And testing, breaking this into small modules is usually a good idea to have smaller units that you can test in isolation, right? A notebook is really not good for modularity. You have individual cells, but you can't really run tests on individual cells, right? So you really want small functions like this with clear inputs, clear outputs that you could test in isolation. Right. I'm jumping around a little bit. Let me come back here to this later. Once you have all these tests, you can automate them. Who has used continuous integration before to run tests automatically? Some of you, not most of you. So this is a GitHub Actions of the world. It used to be Travis CI or other systems. The idea here is pretty much every time you change something in your code base, automatically your tests will be executed. The very early days of testing, testers were mostly humans, manually inputting or clicking through things. We still do this for usability testing quite a bit, although even there we try to automate things. We try to get away from humans manually clicking on things or executing functions with different. Right, the next step was to write these kind of tests, as I've shown you before, these unit tests. But then the challenge was often, oh yeah, there were a bunch of unit tests, but nobody was executing them, to be honest, right? It's Friday evening, I want to go home. Let's just push the code. It was very common to break the code, to check something in that would break some test cases. There were a lot of attempts early on at kind of social motivation. Like if you broke the build, you had to wear, there were hazing rituals. You had to wear a Britney Spears t-shirt for the next day or a hat that you broke the build or something like this. Continuous integration avoids that. Continuous integration means that whenever you push the code, before it's integrated, it gets executed, all the tests get executed. And if the build breaks, if a test case fails, you tend to not merge it. Right? You have a check. Research there essentially shows the main benefit of continuous integration is not the automation or anything. It's just that the tests actually get executed. You can't forget to run the tests, right? You can't just write code for a while and push things and then you have 1,000 tests to fix. You run them much more frequently. It's not that people write more tests necessarily. Continuous integration in itself is not particularly fancy, right? So the test always has these ingredients of you have a test function, you have some sort of test set up, you run something, and then you check whether the outputs are correct, often with some helper methods. The smaller the units are, the easier it is to write test cases for. It's easier to observe. But it requires some skill to write testable code. So again, notebooks are these very long methods, or not even methods, that are very hard to test because they are long. But you can also write outside of notebooks very big functions, very deeply integrated functions that are hard to test. If you already know that you're going to test stuff, you often write more modular code that's easier to separate, where you need less setup, less abstractions. Right? There's a lot of knowledge here of how to kind of separate functions, make them independently testable. An interesting idea which hasn't caught on broadly is test-driven development. Always write your test cases before you write any code. So if you take this strictly, you never write any code unless you have a failing test case first. So if you were to write, too far back, if you were to write this function to massage some code, you first write your test cases describing what you expect the output to be. There's no function yet, so it will fail. And then you write the function until this test passes. And then you may write another test that explores corner cases, and only then you implement the mechanism. People don't do this very often in practice, but if you do this test-driven development, you write the tests first, and you really think about, how can I test this so the code that you're testing is going to be necessarily much more testable, right? Because you think about how I can test this, it needs to be smaller, more abstract, more testable in isolation. Continuous integration testing systems often also allow you to collect statistics, either in the log files or in some external things. For example, look at coverage statistics over time, look at who breaks the build the most, how long does it take. Coverage is a common example to see how many lines of code has been executed by a test. So you may have a large project with several thousand lines of code, and there's one part of the code base that you test really well, and a lot of code that you don't. Coverage is a very simple metric to see what has been tested at all. It doesn't really tell you whether it has been tested well, but it will show you all the places where you have never even executed it during testing. So the simplest form of coverage is just to collect which lines of code have been ever executed at least once by any test case. There are lots of tools which will just do this for you. If you use PyTest or unit test in Python or something like this, there's going to be a coverage tool. We're going to show you this also in the future, lab, that you just run it. You don't really change your code in any way. You just run it with coverage enabled. Most IDEs support this too. And it will just show you which lines have been executed when you executed the test. In an IDE, it will often show you in green background color, this line has been executed, in red, this one hasn't been executed. And then you get summary statistics where you can see, so in some of these files, every single line has been executed, and some less. Doesn't mean that you need to actually execute every single file or that executing each line once is sufficient, but it gives you some idea of blind spots, and it's a first attempt of actually monitoring, are we testing any code that we're writing? Does this make sense? In the second milestone, we're going to make you test your data wrangling code and ask you to also collect coverage.
Do you think like a certain benchmark for coverage, like you should always hit? Because like sometimes more coverage isn't always better, but do you believe there's a certain like bare minimum?
So when I teach a full testing course, I would usually say if you are in a company where somebody asks you to achieve a specific amount of coverage, whether it's 100% or 80%, quit. They don't know what they're doing, right? So coverage is not a super meaningful metric in itself. It's an indicator. And I think also, we'll come back to this, when it comes to data science code, you don't need to test each stuff equally. So data wrangling code is where most of the mistakes are, like feature engineering, data cleaning, things like this. You don't really want to test the machine learning code itself, especially not the libraries. You don't test whether pandas works, right? So there might be code that is also setup code, or that's just not relevant, or you're confident that it doesn't matter as much, right? So it's very hard to say, like 100% coverage is just mean. We sometimes do this in homework assignment just to kind of for students to experience how hard it is to get there, and also what kind of meaningless test cases you tend to write to just get there, because you just execute this and don't care about the output or so, right? Just to make sure that something gets executed. But looking at coverage outputs can be helpful to discover blind spots. Like something like 80% is typically a good value for most projects, but again, it depends a lot on the project and how important it is, right? Is there something like coverage for model testing? So Bogdan talked last lecture about how you can be more careful about model testing, think about slicing, think about behaviors that you want to test. Is there any notion of coverage? How you know how good your tests are? How complete your tests are? So if you want to test a model, what's the line there?
The fit is just like one line out of everything else that you're doing.
Oh, so the pipeline code you can do, right? The pipeline code, the code that trains the model, the code that does the feature engineering, that's just standard code. But the model itself, the pickled model, the thing that runs the inference, we want to know, does it detect, does it use gender, does it use the experience level, right? These kind of things. Is there a notion to measure coverage?
We can maybe use mutations for a particular input to test.
What are you testing for?
It depends on the model, but
Maybe slices the way we did.
How do you know whether you're done, or do you count the number of slices as coverage, or do you know how many things you did not cover with slices?
We have two examples from the Excel writing at Microsoft. One is, let's say you have a taxonomy of use cases or user scenarios. So you can compute test coverage relative to that. You know, to what extent do you cover all of the common usage scenarios? You do slicing on that if you want. You know, to what extent do you cover scenarios that you care about more or less, and so forth. The second example is you could do this with respect to telemetry data. You know, let's say you have a version of the thing out and you have telemetry from it, you can compute coverage of your test cases for the next version relative to how people are using the current.
So to kind of put it around what Bogdan said is, you're doing coverage typically with regard to requirements, some sort of notion of these are all the behavior that we want to support, which might come from, we said in Excel, from a list of behaviors, a taxonomy, or you discover this somehow in production, what are all the things that we want to do. And if you have a list of behaviors, you can check manually essentially against them, right? We do this in software engineering kind of to specification coverage, but it's manual. So you can think about, here are all my requirements. Have I tested this requirements? Have I tested this requirement? Have I tested this requirement? Because it's manual, because there's no automatic tracing, people don't really do that much and don't report coverage. People like coverage like this because it's completely automated. You just run your tests and you get the numbers as a side effect, whether it means something or not. People have tried some sort of mutation coverage or some sort of neuron coverage. How many different neurons or pathways in the decision trees have we executed? This was never making a lot of sense to me. I haven't found this particularly useful. So I think the only thing that we have on the model side is a more manual thing where we have some sort of ground truth of requirements, which usually we don't have. So I think it's very hard to approximate this. This is what a lot of practitioners are trying to do. Are our tests any good? Especially if you try to do more behavioral testing, but it's often in a reaction to mistakes that you already know, or in some cases where you have some existing taxonomy or you have somebody who's done some research. Make sense? Let me come back to this part. This was your reading also. This is the same team at Google that did the MLOps paper. So this was actually follow-up work where they realized, oh, there's so much stuff that we can test, right? So in the reading, you saw these things of all these things that you can do test on data, like is all the feature input code, has this been tested? That's kind of the data wrangling thing that I've shown you, right? Or new features can be added quickly, like our infrastructure is flexible, or offline and online metrics correlate. A simpler model is not better, right? All kinds of simple tests, infrastructure tests that the training is reproducible or the model is debuggable, monitoring tests, the monitoring actually works, right? The models are not stale. So the paper had all these different tests. I want you in small groups to think about, in a concrete system, what would you test? As a case study, let's say we use a smartphone app to detect a disease. This was from a midterm in 2020. So we used COVID back then and pretended with a smartphone by breathing into the microphone with a smart model, you could have a pretty decent chance to detect COVID. This is a colleague of ours that does something similar for other diseases. Again, by breathing into a smartphone, can fairly reliably detect certain kinds of lung diseases. So let's say you want to, no, I didn't want to show this actually. So let's say you're building this app and you're deploying this. You have the model on a server, it uploads the audio file, it gets answers quickly. I want you to think about if you deploy this beyond the model, we assume we can test the model, but what else should we test? And I want to divide you into 4 groups here with the 4 chapters of the paper. Think about back parkside data tests, like that section of the paper. Like, what are the possible things you could test and what do you think is important? Maybe sketch a tiny bit of code of how you would actually test that. Doesn't need to be runnable code. Model development tests, infrastructure tests, and monitoring tests. All right, Bogdan, can you find a volunteer? I think we need a volunteer from each corner of the room now. You talked about model development. What could you test? What do you think is important to test?
So we thought of maybe testing if the model can. So we thought of testing if the model can work on the different device operating system. So Android, iOS, and then testing to see if the accuracy is.
So testing deployment on different devices and whether that makes any difference?
Yeah, the model, if it works on.
Okay. Yeah, so just the deployment infrastructure, if you were to deploy the model actually on the device, which you could, maybe. Okay. Any other model, same group, any other model development thing you would test? What did you talk about?
So basically our team point was about false negatives, about like based on like gender, race, or accent. So this was the.
That's testing the model though, right?
Yeah, we talked about it.
Right. I wanted you to think beyond testing the model itself. What can you test around the development of the model? Right, so you could go through this list here and think about, is a simpler model better, right? That's a very simple thing, like have some sort of basic baseline and see whether that's better and have an automated test for this, right? Can you maybe pick another side of the room? This is data tests, right? What kind of thing did you talk about?
we talked about just like validating the audio or like the sensor data quality.
So having some test of audio quality, of the sensor quality, okay? I'm not sure how you would test that, but there's probably tests for that. I believe you. Anybody else? Data quality or data tests?
We were talking about privacy control of all the data, all the names.
How would you test that?
Just going through. We remove out.
Okay, so this was a privacy control. You write a function to remove identifying information, and then you test whether that works. Kind of, this is non-machine learning code. You could just test. Okay, sounds good. Can I get somebody from the front? Sure. This was infrastructure tests, I think, right?
Yeah, this is about. We discussed mainly reproducibility.
Okay.
We want to maybe make sure that if you run a test in the morning, you get one diagnosis. After lunch, you have another test. Ideally, that should be the same diagnosis.
Yep. How would you test that?
However, I think that maybe same data or same sample, run it on these different times or scenarios, and actually probably the same result.
Yeah, either train the model twice or train the model in like compare the model trained now with the model trained an hour ago, right? And then essentially just compare accuracy for the same inputs, like how often does it flip? So you could do something like this to see how reproducible it is. And then maybe you had the, which one, monitoring tests?
So we thought that there's like a couple of things we can do. First is once the model's been deployed, we monitor, we test for what the latency is for inference, because if we keep retraining the model, it goes high, inference times run up, so you want to that.
Yep.
The second thing was during model training, we monitor and test for exploding and vanishing tokens. So we came up with these two primarily.
Right, so this is monitoring things. Can you also test your monitoring system?
Yes.
I'm actually going to talk about this in a minute. Let me get there. All right, so I think what I try to do with this breakout is to give you a sense that there's so much more to test than just the model, right? They realized this too. They had this whole rubric, and they kind of try to enforce it in the teams by training them, scoring them, essentially, how many of these tests are you running? And some teams are more mature in terms of testing, right? The point is really test code beyond the model. Test all the code that connects to other parts of the pipeline, right? The data ingestion, the monitoring code, the deployment code, and so on. Don't want to play that video. So just briefly in the last couple of minutes that I have, I want to show you two ideas in this space. One is testing testing code with dependencies. This is a standard software engineering idea. If you have code that you're testing, like the data wrangling code, that's launched by some other code, it's needed by some GUI or by the pipeline code, and it relies on some other code, like a database. How do you test that? Right? Do you first need to start a fake database with some fake data and then have a user click a button? Probably not. You want to automate this more, right? So you want to only test this part in the middle, even though it has dependencies. The first part is easy. Rather than clicking a button, you want to write a unit test, right? So we don't want to test this by clicking a button in the user interface. We just write a unit test that we can automate. So we replace the clicking or wherever it came from just by a test driver, standard unit test. But then what do we do about the back end? So we want to program the actual code runs against this database. Does it mean we need to run the tests against the production database? Do we need to set up a fake database? How do we deal with that? And the standard approach here is to create a stub or a double to have something where you can use the database instead of the dependency. So you don't actually use a real database, but you use a fake database that ideally has the same interface. There's a running example here that I probably don't have time for. But for example, you could just have, instead of a database, you have a hard-coded data frame that just has certain values in the database. So you don't need to launch the database, and you certainly don't want to run this against production data. Typically, what you do is, for this data access thing, you have an interface, and then you have different implementations of that interface. You have the thing that you use at runtime, the actual database. So this could be look up a row, right? At runtime, you use a real database. During testing, you provide a fake implementation of that that always returns the same row every single time, so it's reproducible. Right? So again, this kind of idea where here's a model stub. In this case, we're replacing the model. We're not testing the model, but the other code around it. So the model always returns a fixed value independent of what the input is, so we can test the rest of the code. Does this idea in general make sense? Right? So you have code that relies on something else, but you're not testing on that. You're testing against a fake implementation of that. And now you can use this also for testing error handling, because now you can pretend that your fake implementation of the database has a problem. It's typically pretty hard to test for connection errors or random mistakes that happen, like network disconnected. You don't really want to unplug the network while you're running a test, right, every single time, or write code that shuts down the network on your machine. So a much easier way to do this is inject mistakes. So first of all, you just test for certain functions, you expect a mistake as an output. So this is how in Python you would write code that tests the result of this should be an exception. Right? Whenever I run this, this should not succeed. I want an exception here. And then you can, this is way too much code. You can test error handling mechanisms. So here's way too small code. You can look at this later if you want. But the basic idea is that there's a database connection here or a model connection, some connection that we stub out, that we provide a fake implementation. And what this thing does is if you request something from that connection, it raises an exception the first 2 or 3 times you try. Right? So you have essentially an unreliable connection, or a connection that's reliably raising an error. So you can test your error handling mechanism. You don't test against the real system, but you test against an implementation of that component that raises a mistake. So here, the thing that this code's supposed to test is a retry mechanism. If you implement a retry mechanism that tries 3 times to make a connection, you can test that it's actually successful by having this fake implementation of a connection that fails on the first 2 attempts and then succeeds on the 3rd. So your entire test passes if you put in that fake connection. Right? And if you have one that fails 4 times in a row, you would expect this to fail. Right? So you can test your retry mechanism like this. So pipelines often have all these steps and all these connections. So testing error handling for all these parts, these external data sources, or uploading a model somewhere, make sure that you actually recognize when the upload fails. If you're trying to get current data, have a mechanism to detect that the data is current, right? That the database connection or the file has been updated, and test that this mechanism actually works. You can also log mistakes and analyze error logs. You can even test monitoring systems. This is a little bit more sophisticated, where you have a monitoring system and then you inject mistakes and see whether the monitor detects it. You can intentionally shut down a system and see whether the monitor system raises an alarm. In practice, this is hard to do with unit tests. So people tend to do this much more in production these days. And this is where the idea of chaos engineering, which I guess I took out, comes in, where some systems will actually take down systems in production. So if you're comfortable enough that you have implemented error handling, you can carefully try to test this in production, where you actually take down a machine while it's running and see whether your error handling mechanisms work. You hopefully want to be quite confident at this point, and there's all kinds of ideas of minimizing the blast radius, that it doesn't have too many consequences. It's essentially a fire drill, right? So you essentially intentionally introduce a mistake in a runtime system and expect your monitoring systems to alert this. Not something you want to necessarily automate fully, but there are systems. Netflix has a lot of success. Bogdan will talk about this in next Monday, I think, in the testing and production lecture, that actually take AWS systems down in production for Netflix, just to see whether the system is robust and you don't get interrupted when you're watching a movie. Quickly, where to focus testing. I mentioned this earlier. Focus on the things that you write that deal with data wrangling and that focus on things interacting with other external services, right? Make sure that connections you detect when something is wrong. The error handling code is very important. And otherwise, everything that manipulates data. So when you're doing this in Milestone 2, you get data from the Kafka stream, for example. You're processing that data. This data processing code, you actually want to test, right? Is it still working if the data isn't quite in the shape that you expect it to be? Will it crash entirely? Do you have a way to recover from that? So that's usually where it's, when you think about a pipeline, that's probably worth spending most of your time. And then just very quickly to get to at the end, there are also forms of looking at code that are not testing. Code review is a common thing. I guess if you've done any internship, you run into code review, right? Where you submit code as a pull request or in some other form and somebody looks over it. It's not super effective at finding mistakes if people study this, but it can find some mistakes. And effectively, what we did earlier together was code review. We collectively stared at the code and found mistakes. And collectively, we were not very effective at finding those mistakes, right? So testing is often better than just staring at code. But staring at code is an option and is something that a lot of organizations do. Has also other benefits of collective code ownership, and everybody is aware what other people are doing. If you believe Bogdan, this is all going to go away and LLMs will review your code. Maybe they are going to be better at finding bugs, but you lose all the other benefits, which maybe is good, maybe it's not. I don't know. Static analysis is another thing that can find certain bugs. Static analysis will essentially look at the structure of your code without running it. That's why it's static. Testing is dynamic. It's actually executing the code. What's the problem with this code? There is nothing. Depends on the language, but C and Java and everything, this would assign the value, not compare the value, right? Equal versus equal, equal. A static analysis tool can just look for this pattern. Do you ever have an if statement with a single equal in there? It's most likely going to be a mistake. There are cases where this is valid code and what you actually want, but I think very rarely. Like this code always evaluates to true. So this if statement is kind of redundant. What's the problem with the lower code? It just has dead code down here, right? This code is never executed. How much you consider this as a problem, I don't know. Java would complain and let you not compile this. I think Python doesn't care. You just have it in there. Again, a static analysis tool can detect dead code very reliably. This is something that a compiler will do internally, like in Java. Just figure out, is there any path to the code that's not reachable to essentially create a graph? So static analysis tools exist and have been around for a long time. They can find patterns. There are some specifically for machine learning code. For example, all of these, this we found with dynamic analysis, but there's a bunch of tools that find common patterns in data science code, like fishy assignments, wrong use of tensor shapes in TensorFlow. They're not super popular. The more common one is code style issues. What's the standard Python thing? Flake 8, I think, is a common tool that kind of figures out whether your code is formatted well and whether you have some common formatting issues. But these kind of tools exist. So anyway, to summarize, where I wanted to go today is really, we started by testing only the model behavior, but there's all this code that goes into creating the model and running the model in production. And that code often has mistakes too, and those you might want to test too. To do this, get out of a notebook, modularize your code, write unit tests. There's lots of techniques around. You can test robustness, you can test error handling, and we're going to make you explore some of that in the homework. All right. See you Wednesday.